So now the program is going to start focusing much more on those timing issues and functions and processes that are specific to the financial marketplace. Up to now, we've been talking about timing in general, GPS, vulnerabilities, what the regulatory agencies are doing. It's my pleasure to introduce Matthew Knight from Metamako, who is going to talk about the Metamako products. Matthew, thank you. How to use this thing?
I'll work it out.
Push the green button.
And if I need to go back, I will do it.
Yeah, you got it.
Sounds good. Thanks, Pat.
You bet.
Just going to set my timer up so I know how long I have. Oh, perfect. Okay. I'm sorry to drag you back from your break. So my name's Matthew Knight. I work for Metamako. Last year you had our founder and CTO, Dave Snowden, up here, but this year it's me. So I'll do my best to fill in. So I'm going to be talking about a project we undertook almost a year ago now, which was to, okay, so taking a step back, I'm just going to give you an overview before I dive in. There's a lot of devices out there that will timestamp network traffic. And I mean, you know, there's really good, like any industry, there's really good ones and some are less good. But the issue that's bothered us for some time is the fact that, you know, they'll give you a timestamp and you can timestamp two events a certain time apart and work out how long something took or an interval or a latency or whatever you want to call it. But to the best of our knowledge, there was never anything out there that told you how accurate the timestamp was versus its time source, right? So some clock is timestamping, you're synchronizing the clock from something. Well, how accurate is the timestamp relative to the signal being used to synchronize the clock? So we kicked this off by saying we want to solve that problem. And this really is the story of how we did. So, quick blurb for Metamako. Who are we? We've been around since 2013, headquartered in Sydney. We've got. I'm afraid the slides haven't come through as well as they should have. We're not a PowerPoint company, so there was some glitches in the conversion. But you know, we're quite big in the electronic trading world, though our products do have use cases outside that, and we'll continue to. We expect to see more growth in that area, hopefully in the timing market. So what do we do? We're a shop that produces hardware. We're sort of network switches in a way, really focused on very low latencies. We're also an FPGA platform. We've also got applications we run on our platforms. The first product was really the layer 1 switch, which really is just a very fast way to take streams in, replicate them, and push them out again, as low as 5 nanoseconds in our case, which, when you think about it, is the same length as about a meter of fiber or copper. But we've expanded from there, and we then added a MUX to do order entry, so sending multiple streams down into one, and we also branched out into the packet broker / tap aggregation market. And as I said, we're also an FPGA platform. So I'm going to talk a little bit about MetaWatch, which is the product that we benchmarked here. So MetaWatch, it can run on a number of our platforms. We've got several. Specifically, we used our 32-port box to do this. We also have 48 and 96-port boxes. And MetaWatch's claim to fame is a couple of things. One is, you know, we've really striven very hard to have very high precision timestamping. We have a resolution of 1 nanosecond, and we'll see whether we have an accuracy of 1 nanosecond in a little bit. And we've also got very deep buffers. We have up to 32 gigabytes of buffer. So if you're ingesting multiple 10 gigabyte streams and you want to aggregate those streams, in our case, you can aggregate up to 15 to 1. you have a lot of buffering to handle scenarios where there's simultaneous traffic on multiple ports. So it means ultimately, if you're doing aggregation tapping, you have the benefit that, yes, there still can be loss. I'm not going to pretend that we're lossless, but you're really minimizing the probability of loss. To put it into perspective, a lot of the commercial switches out there that do this typically are ASIC-based, and they may have in the region of 10 megabytes of buffer. So we are 3 orders of magnitude greater than that. The other thing is we have an integrated tap, meaning you can go into one port and come out another, 5 nanosecond penalty, grab a copy, timestamp it, whatever. So here's a diagram just sort of illustrating what I'm talking about. We've got, our 15 10 gig ports going through some very, very small edge buffers, and then going down a big pipe to a 16 gigabyte DIMM in this case. We support smaller sizes as well. And we've got 2 of those on each device, so that's essentially duplicated twice. So, in summary, it's up to 300 gigabits a second ingress to 2 by 10 egress. We also support IEEE 802.3x flow control on the egress ports, which is interesting because it means that because we've got these deep buffers, if your receiving application can't keep up, drinking from a fire hose of aggregated traffic, you can send pause frames back and we'll honor them. And what we'll do is we'll just hold stuff in the buffer. Clearly, it could cause the buffer to overflow if you've got a very slow consumer. But in a lot of cases, it's much, much better than something just spewing out data, and if you can't keep up, you have to drop it on the floor. So that's something we've implemented quite recently and is interesting. So again, the goal here is to provide very accurate timestamps and absolutely minimize the potential of dropping packets. I'm going to talk a little bit about STAC now, because we worked with STAC on this benchmark and some other benchmarks. We're a member of the working group on this. Peter, sitting over there, is the founder of STAC, and we've known each other for a few years now. And ultimately, if he can tell you far more about them than I can. But ultimately, in this industry anyway, from a timestamping and from a sort of metrics and performance point of view, STAC is very much a leader in providing unbiased technology research and the ability to sort of design benchmarks to measure a lot of different things. And hence, we wanted to work with STAC on this one because, I mean, we could certainly do it all ourselves, but it's us telling you how good we are, right? And that's never as good as getting an independent opinion as well, a trusted independent opinion. So I'm going to introduce the TimeSync STAC-TS benchmark suite. There are more things in there than that. I'm just focusing on the ones that relate to accuracy and for devices like ours. So we went through the suite of STAC benchmarks, and the key ones that I'm going to talk about are PSE1, PSE2, and NTE2. So starting at the beginning, PSE1 is basically sending the same thing into any 2 ports of a device in theory, and it will tell you whether you get the same timestamp. If you send the same frame concurrently into 2 ports, ideally you get exactly the same timestamp every time. Now the vagaries of FPGA routing and so on mean that isn't necessarily the case. So this is a benchmark to show, well, if I want to know how accurate across my ports I am. PSE2 is very similar, but the difference here is instead of having 2 ports on the same device, you have a port into each of 2 identical devices. So now you're making it a lot harder because each device has its own clock, which needs to be synchronized to the same reference. So the source of error isn't just internal to the device, it's how well does the device sync to an external reference and the other device sync to that same external reference. And then finally, NTE2 was the big one from our point of view. It's quite a big and involved test, and I'm going to spend a lot of time on it, well, as much as I have. And that really is how accurate is a timestamp to the external reference directly. So let's start with the results. I'm not going to spend a huge amount of time on these. It's more about the process. There's a report available on the STAC website from STAC that's available on our website as well. But I put the results up just so you can all sort of see, where more or less where we are. So, we see here any two ports on the same device, worst case, are plus or minus 5 nanoseconds apart. And that was over a huge sample. I believe it was in the order of 60 million frames. Am I right, Peter? Was it 60 million? Yeah, something up there. It's, so statistically, it's pretty averaged out. And the absolute worst case was plus or minus 5. And in the best case, it was actually as low as plus or minus 1. Now, there was a slight amount of skew between different ports, so obviously you get different results depending upon which 2 ports you choose. So that's factored into there as well. But the way STAC does it is it's a total. And for PSE2, very similar, same test, but we see that the error is slightly higher at plus or minus 9, worst case. And again, that can easily be explained as that involves 2 devices synchronizing to a common reference as well. Right, let's talk about NTE2 now. So this daunting diagram is the sort of rig we had to put together to do it. And I won't go into too much detail, but the key points are that the premise of this test was you need something in the time domain that can timestamp network packets and simultaneously timestamp a synchronization signal. In this case, we chose a standard 1 PPS pulse, which is typically a 5-volt rising edge at the start of a second. And there's a number of ways to do this, but the one we chose and the one I think was the right choice was we used an oscilloscope, because their job is to synchronize channels in time, sampling exactly the same time across different channels. So to do that, though, and this is the tricky bit, top right, well, sort of top middle, was we actually fed 10 gig into the oscilloscope. So 10 gigabit is a carrier frequency of 5 gigahertz. It's modulated, and you need to sample it at least 10 gigahertz. So, and then you have to convert the voltages into ones and zeros. And then you have to apply the 10 gig decoding and so on. So it's quite an involved process. But by doing this, what we're doing essentially is we have our device in the middle, marked the dot, and we send the same frame to the dot and to the oscilloscope simultaneously, and we send the same timing pulse to the dot and the oscilloscope simultaneously. And then we compare the two within the oscilloscope and then work out what the timestamp should be and then compare it with what the timestamp we actually put on was. So this was quite a daunting test. So visually, what I just said, a stream of 1 PPS pulses. We used a rubidium frequency reference, free running, which was more than stable enough for what we were doing. So we sent the stream of PPS pulses in to both devices, and we sent a stream of 10 gigabit frames into 2 devices. And we actually self-measured ourselves. There was a subtlety in that we wanted to measure every millisecond, so we also sent a stream of 1,000 PPS in. And we'd acquire every millisecond. So we're measuring throughout the whole duration of a second. We're not just measuring a short burst at the beginning of the second or the middle of the second or whatever. We're measuring over multiple seconds every millisecond. Key elements of interest, as I said, up here we've got some of the components we needed. We had the frequency generator for the 1,000 hertz pulse. We've got the rubidium. We had a sort of high-end LaCroix oscilloscope, and then some custom equipment at the bottom. What you're looking at is a way of converting an Ethernet SFI signal, which is the 10 gig signal that comes out of the back of the transceiver, into something that you can feed into an oscilloscope. So this is what we captured. This is what 10 gigabits looks like. The top is at coarse range, and the bottom is magnified. It's the yellow bit. And you can see here that 10 gigabit really is, it's just, if a 1 is a high voltage and a 0 is a low voltage. And if you've got multiple ones, you get a wider wave. So you can actually see how the encoding works. Though we didn't do the decode ourselves, we used LaCroix's decode that knows how to decode its capture of 10 gigabits. And here we see at the bottom, we have the decode table that's actually highlighting that each of those purple areas is an interframe gap, and we see the starter frame at the end of it, and it tells us exactly what time with massive resolution. That's down to picoseconds. So it wasn't all smooth sailing, as you can probably imagine. There were some highs, the negatives were it took a long time to download the decode and so on, so it made test runs, and we did a lot of them very, very slow and standard, very, very slow. The other thing is the standard oscilloscope has quite a small acquisition buffer. We needed a very big acquisition buffer because it was sampling so fast. But we got there in the end, and this is what the end of a run actually looked like. We had at the top, you see the various different channels. We've got 2 channels of Ethernet because it's differential. We've also got the second one down is the 1 PPS pulse, and the bottom one, magnified here, is the 1,000 PPS pulse. So, and we see under it, you see the decode where it says block payload. It's actually telling you, byte by byte, what's coming in off the wire. So 3 sets of runs were done, and the reason we did that was the Ethernet standard says that your Ethernet transmit clock can vary in frequency. There's no frequency locking in Ethernet. The standard says your Ethernet clock must be within 100 parts per million of where it should be. So the clock can be anywhere in there, and 100 parts per million, defines things like, your transmit clock comes in, your receive clock comes out. And the way Ethernet works is there's something called the interframe gap between different frames, and it can be squeezed if the incoming clock is faster than the outgoing clock to stop overruns, right? And obviously you can make it bigger if you need to. So it was very important, and this was contributed by one of the other vendors in the Benchmark Council, that we measured at the extremes. So we actually did 3 sets of measurements, one at a nominal Ethernet clock, and then one at the clock speeded up by 100 parts per million and then slowed down by 100 parts per million. So we did three separate runs of each to see whether that had any influence on our timestamps. Because if you're timestamping based on the received clock, it will absolutely have an influence on your timestamps. So here are the results. I've skimmed over a lot of the process and so on, but I don't think that's fundamentally germane. And this is what they look like. Now, I do want to emphasize these are the results interpreted by us. The STAC results are all at nanosecond. They're comparing nanosecond resolution, whereas we used nanoseconds on the timestamp and picoseconds on the oscilloscope. So we binned them into 50 picosecond bins. And I'm pretty happy with the distribution. Unfortunately, it isn't normal. It looks normal, but it doesn't actually meet the criteria of normalcy. And the key result is that, from our point of view, is that 92.3% of timestamps are within 1.5 nanoseconds of the absolute timestamp. So we're synchronizing from an external reference pulse and demonstrating that our timestamps are within plus or minus, all of them are within, I think it was -2 plus, what's the min? -3 plus 2.2 in this case, because it's slightly different to the STAC results because we did this in picoseconds. The STAC results are, I think it's -2.5 plus 3, or the other way around. I can't remember. So overall, we saw this as pretty good. We are demonstrating that relative to your external PPS source, that's how good the timestamps are on a specific port. And then if you combine that with, what if I'm on a different port, then you get the numbers in PS1, or what if I'm on two different machines, you get the numbers in PS2. So, how confident are we that this is accurate statistically and so on? Well, unfortunately, we would have loved to do millions of measurements, but the oscilloscope acquisition buffers just aren't big enough. They'll hold, say, 100 million samples, but if each sample is 12.5 picoseconds long, which is the case, you can't hold that many. You can't hold that many frames. So we were really limited by the size of the buffer, and it was a pretty big buffer for an oscilloscope. But we managed to get at least 1,000 samples of each measurement. STAC were very helpful, Peter specifically, in helping us work out the errors and confirm our understanding of where the errors were. And we actually worked out that our measurement was accurate to 50 picoseconds, which is why we used 50 picosecond bins. So there are sources of error in there. We know what they are. There's a synchronization of the DUT to the PPS signal, sampling error in timestamping the incoming frame. It can be on a clock boundary. It can fall into the next rather than the previous bracket and so on. And there is potential instability in packet sources Ethernet clock. Ethernet clocks can vary quite a lot, and they can be quite jittery as well. So this also was the first time the STAC-TS tests have been run by STAC. We did calibrate MetaWatch for skew. We found out that we were 10 nanoseconds away, and this testing showed us that. So we have a compensation factor that we put in now. And from our point of view, the timestamps were proven to be very accurate. And going back to earlier talks, yes, we do exceed the current trading regulatory standards for timestamp accuracy, which is quite nice. I think that's it. Questions, if any?
We have time for one question.
Hi, I'm Mark Weiss. I'm consulting with Booz Allen. I was stunned in the earlier talk, I think it was Austin Garrig, when he said that there are no requirements for timestamp accuracy in the U.S. requirement standard, the CAT NMS. What does that mean, and how can they not require timestamp? I mean, do you know? And here you are measuring timestamp accuracy. Do they need to comply in some level?
I'm afraid I'm not a regulatory expert, so I can't give you a hard answer to that one. But my understanding is there is some accuracy requirement. There just isn't a traceability requirement. Is my understanding of it, which I think is kind of ludicrous because, hey, we're accurate. Well, prove you're accurate, right? And that's not there. So yeah, I concur. It does seem a little bit strange, but like most things, I assume it'll get cleaned up, as something comes along.
But I assume you have clients or people who are interested in this work you're doing. You're doing it for someone.
Yep.
So I'm wondering, you must know something about what they want by showing accuracy.
Well, a lot of this there's a lot of applications out there, but very specifically to the electronic trading world, trades are becoming faster and faster. I mean, there are now trades out there, and possibly even lower than I know about, but there aren't trades being turned around in under 200 nanoseconds. And if you're turning a trade around in 200 nanoseconds and you want to measure what your trade latency is, you need something like this, because it's going to get lower. I mean, it's entirely theoretically possible that people are trading in under 100 nanoseconds. It would be difficult, but it's not impossible. So, for one thing, it's the people wanting to measure their accuracy very precisely. You can also use us to do, it's funny, you can also use this level of precision to measure the length of a cable if you want to. What's the propagation delay down this Ethernet cable? We can tell you. So we have clients who use it for a lot of things, but I think the thing they really appreciate is that we've taken the trouble to have an independent test of how good we are, and they can drop it in, and they know it's going to be future-proof for quite a long time. I think that's really the driver. That's the feedback. Thank you.